So the equations we will be using are the one for impulse, which is represented by J, and that is the change in momentum. And so it would be J equals delta P equals M delta V. The next equation we will be using is one of the kinematics equations. V final squared equals V initial squared plus 2A y final minus y initial, and this we will be using to solve for the velocity. So the units that we will be using are for mass is going to be in kilograms, and then for the height, which was represented by the variable y, we will be it will be measured in meters. Velocity is measured in meters per second. Acceleration, we will be using the free fall acceleration, so it would be 9.80 meters per second squared. And then for our final units, momentum is measured in kgm per second, and then impulse is measured in Newton seconds. So to find the mass of the tennis ball, we used a scale or a balance, and the mass ended up being 56.6 grams, which converts to 0.0566 kilograms. And now to find the velocity when the ball is going down, because we're dropping it from a height of 99 centimeters, which converts to 0.99 meters. We use the kinematics equation. And since we're dropping it down, initial velocity would be 0. And so we just have to measure the height, which, as we said, we dropped it from a height of 0.99 meters. And now we just plug all the numbers in, and the velocity turns out to be 4.40 ms. So after the ball hits the tennis racket, it's going to bounce back up, and to find that velocity, we use the kinematics equation again. And the final velocity would be 0 because it stops later on. And then the height, as we measured from the point where the height we measure when it bounces back up, it turned out to be 63 centimeters, which converts to 0.63 meters. And now we just plug everything in to find the initial velocity. And that turns out to be 3.51 ms. So the velocities that we found, this one was the velocity as it went down, and since the direction is going down, it would be negative. And then the velocity we found as it was coming back up, this would be positive because the velocity is or the ball is going up. And now we're going to use the equation for momentum to find it. So when the ball is going down, that momentum would be using the mass times the velocity. This is negative, and so this turns out to be negative 0.246 kgms. The velocity as it goes back up, use the mass again. That velocity, which gives 0.197 kgms. So now to find the answer to our question, the impulse, which is the change in momentum, so we subtract the initial from the final, which would be, as calculated earlier, it was the 0.197, and then minus the negative 0.246, that becomes positive, and then it gives 0.443 ns, which is our impulse.
Alright, so here are some worked examples. If we have a bullet here that is traveling this way at 500 meters per second and comes to a complete stop right here, because of an impulse of 50 Newton seconds, and we are trying to find the mass of this bullet here. So what we can use is our equation. So we are trying to find this mass. We have the change in velocity here, and this whole thing equals that 50 Newton seconds. So we have the mass, which is 500 meters per second minus 0 meters per second, which equals 50 Newton seconds. So if we take and we divide those, you have 50 divided by 500, which gets you the mass 0.1 kilograms. So for our next worked example, we have a man in a car sitting at a stoplight. So he is initially at rest, and all of a sudden he has this force that pushes him, that accelerates this car to 5 meters per second. So what we were trying to find is the force exerted on the man by the back seat of this car. So to find that, we have our mass times the change in velocity equals our force, which is what we're trying to find, times the change in t. Well, this change in t was given to us. It is 0.3 seconds. So since we have all of this, we have 400 equals the force times 0.3. So if you divide 0.3 from both sides, you get your force, which equals 1,333.33 newtons. So for our first relative example, we're going to use a little baseball analogy. So you got your guy here with his bat, and you got your pitcher up here on the mound, and he's throwing a fastball, and you are hoping to hit this fastball out of the stadium with all these fans, because that would be cool, right? So to use that, we have our momentum equation, M1 and M2. This is the mass of the ball, and this is the mass of the bat, which is going to equal the mass of the ball velocity after the hit plus the mass of the bat. So this is going to be, these two are going to stay the same throughout the swing, because you should continue on throughout your swing. And since this is going to be very large, and if it's a fastball, that's going to be very large, this is going to make the baseball have a very large velocity, and hopefully you'll be able to hit it out of that park. And for our second relative example, we're going to do a little football thing. So we got this big bad running back running with his nice little football right here, and he's really mean. So he has a really big mass, but since he has such a big mass, it takes him a while to get going, so he's gonna have a pretty small velocity. But luckily, we got little baby Zach over here, and he's angry too. And he wants to tackle this big boy. So he may have this small little mass, but he has this ginormous velocity. And if he wants to stop this guy dead in his tracks, he needs to make sure his velocity, these two equations, match.